Now I want to spend a little more time focusing on series that have some negative terms. So pretty much all of the tests we've done up to this point have used strictly positive sequences, right? Where all of the terms in the sequence are positive. We haven't really had a good way to look at series that have negative numbers in them, with the exception of geometric series. Or something that we might be able to write the partial sums of. So in general, an alternating series, the definition of an alternating series is a series that alternates between positive and negative values. So this would be something of the form n equals 1 to infinity of negative 1 to the n a sub n, or n equals 1 to infinity of negative 1 to the n plus 1 a sub n. So the exponent would just determine if you start at the first number or the second number. And then this will make every other term positive. So like this one will be negative a1 plus a2 minus a3, etc. Right? And this one will be a1 minus a2 plus a3 minus a4, etc. So how do we deal with series like this? Okay. So this is known as the alternating series test. And it only requires a little bit, basically one extra condition. So an alternating series of the form, as we just wrote up above, n equals 1 to infinity of negative 1 to the n of b sub n. Books often like to use b sub n for alternating series instead of a sub n. Not entirely sure why they like to change it, but so one of these where you have b sub n converges if step 1, you need to have the limit as n goes to infinity of b sub n be equal to 0, right? So that's just something we always need to have. And then 2, 0 is less than b sub n plus 1 is less than or equal to b sub n for all n is greater than or equal to 1. Okay. So really, you don't even need this to be true for all of them. You need this to be true for all n greater than or equal to some n for some integer n. So just like before, it just needs to be true after a certain point. So what this is saying is that just the b sub n part, so ignoring the negative part, just looking at the numbers themselves, so the absolute value if you want to, those of course would be positive. That's just kind of a given because we're ignoring the negative part. And then the terms need to be decreasing, right? Not strictly decreasing. They can stay the same because of the equality here, but they need to be decreasing, right? They can't be 0. Otherwise, I mean, it's just not an alternating series. But it needs to be a decreasing sequence. So you need to have the limit going to 0 like we always do, and then it needs to be a decreasing sequence, and then it converges. Okay, so let's look at some examples here. So if we look at, for example, n equals 1 to infinity of negative 1 to the n of 1 over n. Okay. Maybe a more common way this might be written. It might not always be written like to the side like that. It might be written just as a fraction, for example. So this is the harmonic series, but now we have alternating terms instead. So this would look like -1 plus a half, minus a third, plus a fourth, minus a fifth, okay, etc. So does this change anything, right? We know the harmonic series doesn't converge, but if we alternate the terms like this, will it now converge? And the answer, according to the alternating series test, is yes, right? So we know that the limit as n goes to infinity of the sequence without the negative part, which is 1 over n, we know that's equal to 0. And we can clearly see that the terms are decreasing, right? Just in general, 1 over n plus 1 is less than or equal to 1 over n, as we've shown before, right? So we have condition 1, we have condition 2, so this does converge, okay? So this is going to be the true with basically any of the p series, right? Because you know any of the p series where n is less than or equal to 1 at least. Or sorry, if p is greater than or equal to 1, the way that we wrote it. Right, so if you have something like n equals 1 to infinity of -1 to the n over n squared, we know that that's going to converge, right? Because that's going to 0, the limit. This is definitely going to be a decreasing sequence, so we know that's going to converge. So I won't go through that one. N equals 1 to infinity of -1 to the n times n over n plus 1. Okay. So now this one's going to fail that first condition, right? The limit as n goes to infinity of n over n plus 1, that's equal to 1. So this does not, well, we can't say that, so I don't want to say it doesn't converge. It means that according to this test, it fails, right? So this test, it didn't give us anything. It doesn't say otherwise it diverges, right? It just tells us that we can't say, we can't even apply the test at all, basically. But because this is also part of the test for divergence, then via that one, we can say that it does diverge, right? So I guess in general, I guess it would be true if this condition fails, of course it diverges. That's the test for divergence. But also if this is an increasing sequence, then it is definitely going to converge as well. I mean, diverge as well. Okay. So we can say the opposite there. So this would diverge. Whoops, let's write one more here. N equals 1 to infinity of -1 to the n plus 1. And that part doesn't really matter too much, right? Like which term it starts at. Again, it would affect what it's converging to, but we're not really looking for that anyway. So this one can be a little trickier. N to infinity of n over 2 to the n. Okay, so here we would need L'Hopital's rule because we're going to get infinity over infinity there. So this will be 1 over 2 to the n natural log of 2. And now this is going to 0, okay, because the bottom's going to infinity. So condition 1 is good. And then is it a decreasing sequence? It sure looks like it is. We're going to have 1/2, 2 fourths. So here it's just equal. That's fine though. 3/8, right? 4 16ths. So it is getting smaller. Okay, so once we can establish a clear pattern here and we can see that it's getting smaller, then that's all we need to do. So by the alternating series test, this does converge.